Piecewise functions, there's a lot going on with piecewise functions. And finding the domain range is not going to be as easy as it was when we did absolute value functions. So keep that in mind. It's called piecewise functions because the functions, the graphs of the functions, literally look like they are broken up into pieces. So instead of we're used to having like a solid line or a solid curve. Piecewise functions is not like that. There's going to be a bunch of different graphs. And each piece of the graph will have its own rule. So because of that, we have to analyze and treat each piece differently. They're grouped together, but they're usually very different. Each equation for each piece is usually quite different than the other ones. Okay. And it's conditional because each piece will only use a particular rule for a certain set of x values. And then for a different set of x values, it'll use a different rule. And we'll spell that all out. Okay. There's two kinds of things that you're going to have to do here. One, you're going to be given the function and you're going to have to graph it and identify the domain and range. And then the second thing that you're going to have to do is they're going to give you the graph and you have to identify the equation. Okay. We're just going to start with an example of a piecewise function. So write that down and I'll explain that all. This is a left brace. So when we do the braces, we just put one left brace. And then below this, I'm going to write out how you should think about this function and how you should kind of read it. We'll write that down underneath. So here's what this means. And I'm going to say it first, then we're going to write it down here. Okay. What this means is f of x equals x minus 2 if x is less than negative 1. So if x is not less than negative 1, we don't apply this rule. But if x is less than negative 1, we apply the rule, basically, y equals x minus 2. If x is greater than or equal to negative 1, then we apply a different rule. You just have to keep it straight. So for one part of the graph, you use this rule. For the other part of the graph, you use this rule. Based on that, how many pieces will there be here? Two. There's two equations, there'll be two pieces. Okay, so here this all means. Here's what you want to think. You want to think y equals x minus 2, and I'm changing it to y, because what kind of equation do I have here? What form is this in? Slope-intercept, right? Y equals x minus 2. For when x is less than negative 1. That's the top rule. The bottom rule is y equals x plus 3. When x is greater than or equal to negative 1. That's how you want to think about these types of functions. I do want to be clear about one thing. Not every problem will have the condition for the top rule and the bottom rule be the same number. This is just unique to this problem. Sometimes it could be less than negative 1, and then this could say x greater than or equal to 7, right? They don't have to start and end at the same spot. This problem just so happens to, okay? Keep that in mind. That you will see it with a gap in between the conditions. But what's important is that the conditions clue you in on the domain, because the domain talks about x. And when you work on those a little more on your own, you'll see what I mean. Okay? At this point, if you're in Notability without graph paper, you might want to turn that on or grab a grid. If you have a grid stored in your photos, use the grid. But you're going to want to do that because we're going to graph this next. On the next page here, now notice I've put a dashed line there. What is the equation of that line? Do you know? It's very close, but it is not correct. I know why you said y equals negative 1, though.
Is it x equals negative 1?
It is x equals negative 1. What is the x value for every point on that line? Right? Negative 1, 0. Negative 1, 1. Negative 1, 2. Negative 1, 3. Negative 1, negative 4. So the x value is negative 1 for every point on that line. Anytime you have a vertical line, it's always x equals some number. And I know it seems backwards, right? Because you're like a vertical line, it's going up and down. We think up and down is y. Well, it's because every value of x on that line equals -1. That's why it comes in the form x equals. So what's the horizontal line going to come in what kind of form? Y equals some number. Okay, let's keep that in mind. Now, this is actually not part of the graph. Okay, this line right here is actually not part of the graph. I put it there just to sort of show you that on one side of that line, less than -1, here's x equals -1, so all the values this way are less than -1. So I'm going to use this rule over here. Then on this side, it's all greater than -1, but I made it even fancier than that for you. Okay? This is how my explain everything skills have advanced over the years. And you can use this way if you want. You don't have to. Okay? Notice I've highlighted the top equation in red. This region is all where x is less than -1. So in the red region, I'm going to use this rule. This blue region is everywhere greater than or equal to -1. So I'm going to use this rule in the blue region. If that helps you to separate your regions, and sometimes you're going to have 3 pieces, and you're going to have a third color. I don't care what color you use. If you want to use another color, it's up to you. You don't have to do this if you don't want to. You just have to know that there is a dividing line where x equals -1 for this problem because of these conditions. All right? Now, the rest of what we're going to do in terms of graphing is old stuff. Slope, y-intercept, find some points, connect them, done. But you have to know that you use one rule over here in the blue, and we use a totally different rule over here in the red, and that's what these indicate. Okay? So we'll start with the red one. And all we're thinking here is y equals x minus 2. And I'm going to keep deleting that because that dotted line is going to show up on every page after this. And then eventually I'm going to stop deleting it because you're going to get the point. Okay? Now, here's where I'm going to change things on you a little bit. Right? The best thing to do to graph these functions is to use the boundaries as inputs. So that's what this says. You're going to start with the boundaries value as an input. All right, so let's look at this red equation. What is the boundaries value for x? -1. The boundaries value is -1. This is what we're talking about right here. Okay, we're talking about this right here. So instead of just making a random table like we did with absolute value, we're going to start with x equals -1. And we're going to plug that in. Okay, and this is what we would get. Plug -1 in for x. Y equals what? -3. So is there a point now at -1, -3?
Yeah.
Yes and no. So now we got to pay attention to this thing. It's less than -1. It's not or equal to. So in theory, I have a point at -1, -3 that I could graph. The problem is -1 is actually not part of this graph. Right? It's less than -1, not or equal to. So how can I put a point at -1, -3 if -1 for x actually isn't on that graph? What do? Nope.
You can't graph it.
Nope. We can graph it. Yeah.
You use the other one that says equal to?
Nope.
Or equal
Because I'm going to use the other rule. Think about number lines. When we were graphing inequalities and we would graph it on a number line, what would we do? Yeah. You leave an open circle. Okay, so the same thing is going to be true here. Even though -1, -3 works for the equation, it technically isn't on the graph. What we do is we put an open circle at that point. Because that's where the graph is going to start, but it's technically not a part of the red piece. Okay, so that's why we make it an open circle. Okay. Now the next part is just using the slope. Use the slope, find some more points, connect the dots, we're done. Okay. So for the red rule, what is the slope here? 1. Okay, so the slope is 1. Okay, slope is 1. But I need a rise and a run in order to find another point. So how would we write it? 1 over 1. Okay. So all I have to do is go from here. I go up 1, right 1. But what happened? I'm in the blue region. I'm supposed to be in the red region. So if I go up 1, right 1, and I did that a bunch of times, I'd be drawing a line in the wrong region. So what do we do? What could we do?
Go down to the left.
Okay, so I can change my slope. How can I change my slope to still equal 1 and make me move the other way?
Oh, 1 and then 1 over -1?
Put -1 over
-1 over -1. Okay? Put both of those together because that still equals 1. So now what that would mean is I would go down 1, left 1. And I'm in the red region still. And I can do that again. Down 1, left 1 until I get a bunch of points. So when that happens to you and you're moving with your slope and you're like, okay, I'm going into the wrong region, you manipulate your slope to work for you. Okay? So all I did again, I realized if I went up 1, right 1, it was taking me into the wrong region using this. That doesn't work. So I changed it to make it -1 over -1, which still equals 1. But now I go down to the left, down to the left, down to the left. And then I connect those, and there's that piece. That piece is now done. The red region, the red rule is done. We finished it. And other than trying to figure out what to do with the boundaries, there's nothing new here, right? Graphing a point, using the slope to find another point. That's why this is in chapter 2, because that's what we were doing earlier. Okay, the slope is not always going to equal 1. In this problem, they're both equal to 1, yeah. But it's not always going to equal 1. And if it wasn't 1, if it was 4, be 4 over 1 or -4 over -1. Yes?
Is that dot on 3?
This one right here?
Yeah.
Yeah.
Okay.
So this is the point, -1, -3. Left 1, down 3. -1, -3. All right, let's work on the second one. It's the same basic principle. Instead of having y equals x minus 2, now I'm looking at y equals x plus 3. And I'm going to do the same thing. I'm going to start with boundary value as the input. So what number am I going to plug in for x? -1. Again, I'm using the same idea here. Oops. So I'm plugging -1 in for x. So what happens when I plug -1 in for x? What do I get for y? 2. Okay. So I plug -1 in, and I get y equals 2. So again, what I really have here is this point -1, 2. I plugged in -1 for x. I get 2. Is this actually on the graph now or not? It is. Why? Or equal to. So that means I can fill this point in. -1, 2. It's going to be up here. -1, 2. I have that point. It's on the graph. What's the slope? What's the slope for this equation? 1. Slope is 1. So now I use it. M equals 1. 1 over 1. Does that take me the right place? Up 1, right 1. I'm in the right region. That's good. Up 1, right 1. So I keep working my way there. Connect the points. There's the graph. 2 pieces, like we said, not connected. It just so happens that they have slope 1, both of them do. That's not how it's going to work out most of the time. Okay? That's the easy part of this problem. The hard part, what do we still have to do? Domain and range. We have to find the domain and range. That's the hard part. The domain and range is going to be the hard part because that whole walls and floors and ceilings concept is still something you're working on. Okay? So let's look at a wall. Let's make a wall. Here's a wall. Let's make it a green wall. Here's a green wall. Oh, I wanted it green. What happened? Oh, I see what happened. Green. Híjole. All right, I almost have it. Green wall, there it is. Is the graph touching that wall? Yep, sure is. Right? Because this right here goes to the left and down forever, so it's going to hit the wall. Is this piece ever going to not hit this wall? No, it's going to hit it. Let's go this side. Is it going to hit the wall on the other side? What happens right here? Here's my question for you. Which graph is this wall currently touching? The blue or the red? Blue. Why is it not red? Open circle. Okay, because it's an open circle. It's not actually touching the red graph. Here's the thing that's interesting about the domain for this. You might think there's an x value that's not on this graph. Right here is the only place you could call it into question. What happens is so if I move my wall, I'm on the red graph, red, oh, jump to blue. But I didn't miss an x value. There's not a gap there. And then it just picks up over here. Okay? What this tells me, if you look at the if statements, it tells me whether or not it's going to be all real numbers. There's not a gap. On this side, it goes all the way to -1, and then when it equals -1, it jumps to here. So there's no wall here at all. The domain is all real numbers. There's not an x value you can pick that's not on the graph somewhere. Every x value that you can think of will be on one of those 2 graphs. Okay? Now the range is a whole different story. Okay, we talk about ceilings and floors. We have to look at each piece differently. Does this graph have a ceiling or a floor? It has a floor. It goes up forever, but it has a bottom. Does this graph have a ceiling or a floor? Ceiling, and then it goes down. So when we look at the range, all of these points in here aren't even included for the y. There's no y here. If y equaled 1, it's not on the graph. If y equaled -1, it's not on the graph. So we have to write 2 separate inequalities to take care of the 1 floor and the 1 ceiling. And eliminate the parts in the middle that are shaded in that aren't on the graph. Okay? So what is the inequality for the top graph for the range?
F of x is
Greater than or equal to 2. That's the y value, right? So right here, the y value is 2. F of x is greater than or equal to that. And it's greater than or equal to because the point is filled in. So how is the inequality for the bottom one going to change?
because it's
Open circle, so it will not have the or equal to. What's this one going to be? less than negative 3. So write my range. I have two inequalities that I have to write. One for the floor for the top, one for the ceiling for the bottom. And basically what that's saying is there are no values for y in between negative 3 and 2, which that's what this shaded in part means. Because right here the y value is negative 3, right here the y value is 2. There are no y's in between, and so by writing two separate inequalities, we've essentially said that. Okay? That's why I said that's the hard part of these problems. Questions? Now let's do the other way. So take a picture of this page. Here's the thing with this problem. First off, how many pieces does it have? So how many equations is it going to have? 3. Okay, so the way I like to start off with these, now the graph tells me what the name of the function is. It tells me that it's f of x. So what I like to do for starters is I want to start with my f of x equals, and I draw a big old brace because I'm going to have room for 3 equations. And notice what I just also did on the graph. I drew boundaries. I drew walls on those 3 pieces. The reason I drew the walls is those will tell me the if x less than greater than kind of statement. That boundary that we have after every one of the rules, if whatever, come from these 3 things. Okay? So we're going to start with the piece furthest to the left. Okay, and if you want to, you can extend that boundary all the way down to the x-axis. Because that's the wall. There's a right wall for this piece. What is the x value for this? 1. So if I wrote a wall for that piece, what would it say?
F of x is
Talking about x, first off. We're talking about x. Raise your hand. Raise your hand if you think you know what the wall would be for that first one. Maddie?
X equals 1.
X, not quite x equals 1. Because you're right. You are right that this line is, the equation of this line is x equals 1. But this graph goes this way. So what are the x values for this piece?
x is
Less than 1. Okay? Or is it less than or equal to? Less than. So I have an open circle here. So it's from here to the left. So that piece is if, and so we say if x is less than 1. Because for all the values where x is less than 1, we're talking about this piece. Because here's a value less than 1, a value less than 1, a value less than 1. All these values less than 1 are going to be on this piece somewhere. So that's the boundary for that first piece. And that's array. Whenever I have array, it's going to be less than or greater than or less than or equal to or greater than or equal to. When I have a situation like this where I have a segment, okay, we're going to write a compound inequality. What is the left wall value? What is the x value of this left wall here? 1. What is the right wall value? 2. Okay? So x there is 1. X here is 2. And since both points are filled in, what does that tell me about what kind of inequality symbols I'm going to have? It's going to have an or equal to in it. Okay? The thing that I like when we put them in order like this is we can write a compounding inequality in exactly this way. So the negative or the 1 is first, the x in the middle, and the 2 on the right. And it's always going to look like this. It's always less than or equal to. Because really, when I look at from the perspective of x, this is saying x is greater than or equal to 1. When I look at it from x. And then this one is saying x is less than or equal to 2, which is what we're saying here. X is in between 1 and 2. We say inclusively because it's or equal to. Question?
Wait, so you said it can only be less than or equal to?
Yes, if you put them in this order where the smaller number is on the left, they'll always be less thans, or less than or equal to. All right, the last piece. We have a boundary right there. What is the x value of that boundary? Okay, before we answer that, let's just extend it down. What x value does it cross? 2. Okay, it's an open circle, and it goes to the right, which to the right means what? Greater than. And this is it or equal to or not?
No, sorry.
No, open circle, so it's not. So what is the if statement for this piece? If x is greater than 2. To me, identifying the boundaries is the hard part. Well, I also think that's going to be true for you. I think writing the equations is going to be easy. Here's why. It goes back to the same concept. You need a slope, you need a y-intercept, then you can write an equation, because all these equations are in slope-intercept form. Y equals something. So understand that that's the concept. We're going to use slope-intercept form, so all we need is the y-intercept and the slope, and we can write an equation. Okay, so let's look at this first one. Okay, this piece here. What is the y-intercept for this piece? Well, what is it? Tell me again what the y-intercept is. What is it? Where the graph does what? Crosses the y-axis. Okay, so here, that's this point right there. What is the y value of that point? 3. So the y-intercept is 3 plus 3. Okay. Now all I have to do is find the slope of that line. So you can just go, and here's what I would do. I would go from here to here. Go up 2, right 1. What's that slope? 2. So how do I incorporate that in my equation? 2x plus 3. All right, first piece is done. See, slope's not always 1. Questions about that? All right. What's the y-intercept for the second piece?
Good question.
Right? It doesn't cross. Whatever will we do? It doesn't cross the y-axis. Okay. False. Here's why. Okay. The rule tells me that it's whatever the normal equation would be, except it's only between x equals 1 and 2. If it wasn't, we could continue it on both directions. So we use the rule the same way, we write the rule the same way as if the line went on forever, even though it doesn't. The conditions restrict it. The boundaries restrict it. So here's what I can do. All right. So to get from this point, because I got to get, here's the thing. The y-axis is over here. So I got to get from here to the left. So if I take this point on the right and I went up 1, left 1, and just did that again, repeat that, right? Because that's what the slope is. I would land on the y-axis. What is the value of that y-intercept? 2. So all I do is I back it up, and then I have a 2. The conditions take care of the chopping the line off. Okay? But the rule is still going to be the same as if the line went on forever. Okay, what is the slope of that segment? Bless you.
X1. It'd be -1, actually.
It would be -1. So if I go from here, I go down 1, right 1. Now I could have gone the other way like I drew it, go up 1, left 1. Still -1. Okay? So what does that do for me in this equation?
It'd be
-x. Okay, last piece before we do it. We talked about it already. You told me already that a vertical line always comes in the form x equals some number. A horizontal line always comes in the form y equals some number. Okay? I have a horizontal line here. What is the value of it? What is the y value that it goes with? 3.
Oh.
Okay, so the equation for this line is y equals 3. So for down here, all I have to do is go 3. Doesn't have an x because it's a horizontal line. Okay, this one did not ask us to find the domain and range. If it did, okay, you'd notice that there were no gaps here. Okay, as I move on the wall, as soon as I get to where y equals 1, it jumps from here to here. So it keeps going, then it jumps from here to here, it keeps going. There's no gap. If there was a gap, you'd see something like, this might be a 4, right? Because here I'm less than 1, then 1 to 2, then 2 to 4. Oh, I skipped a 3 in there, or everything from 2 to 4. That's how you'd know that there would be a gap and the domain wouldn't be all real numbers, okay? But in this case, it is. And the range actually has a ceiling, and that's it. Anyway, you didn't have to do that for this problem.